Conditional probabilities are very useful sometimes in calculating ordinary unconditional probabilities. Remember that the probability of B given A is defined as the probability that both things happen, B and A, the intersection of the two events, divided by the probability that A happens. And if you unravel that equation by multiplying both sides times probability of A, then what you have is the probability of B intersect A is probability of A multiplied times conditional probability of B given A. And we'll illustrate a use of that fact. Let's think about picking two balls from these 7 colored balls shown here. What are the chances that both of the balls that we pick will be green? Let's apply the equation above to the situation where A represents the event that says the first ball is green, and B represents the event that says the second ball is green. In that case, the probability of B intersect A just calculates the probability that both balls are green, the second ball green and the first ball green. And the equation says that's probability of A, which is the probability the first ball is green. Now think about it. When you draw the first ball, you've got 7 balls to draw from, and 4 of them are green. So that's 4 chances in 7 for P of A. Probability first ball is green. And then that next term, that probability of B given A, in this example, B given A says what's the probability that the second ball is green if we know the first ball was green. Well, knowing the first ball was green means there's only 3 green balls left when you draw the second one. And there's 3 red balls also, so that's 3 green balls out of a total of 6 balls. So when you draw that second ball, that's 3 chances in 6 that the second ball will be green if you know the first ball was green. And when you multiply those fractions together, 12 over 6 is 2, divided by 7, 2 sevenths. So the probability that both balls are green is 2 sevenths, and notice we calculated that by using conditional probabilities, even though the question itself does not involve conditional probability. We can extend that line of reasoning to more than 2 events. Suppose, for example, we were picking 3 balls instead of 2, and we were asking the question, what's the probability that all 3 are green? Here we're talking about 3 things happening, the first ball being green, the second ball being green, and the third ball being green. In this example, we need to extend this equation above to 3 events instead of just 2. And this is the way it would look. It would say the probability of all 3 things happening is the probability the first thing happens times the probability the second thing happens if we know the first thing happens, times the probability of the third thing happening if we know that both of the first 2 happen. So if we take another look at the set of balls that we're dealing with, the probability of all 3 things happening is simply the probability the first, second, and third ball are all green. And that's equal to the probability the first ball is green, which is 4 chances out of 7, times the probability the second ball is green if we know the first one is green, And knowing the first ball is green says when we get to the second one, we still have 3 green balls out of the 6 remaining balls. And if we know both of the first 2 balls are green, then when we get to the third ball, there are 2 green balls and 3 red balls left. So that's 2 out of the 5 remaining balls are green. So let's multiply that out. The 3 and the 2 cancel with the 6. And we have 4 over 7 times 5, 4 divided by 35. So that 4/35 is now the probability that all 3 balls are green.